Hello everyone, this is Tiantian from Microsoft Research Asia. Today I'm going to talk about our SIGGRAPH Asia 2019 work, a scalable Galerkin Multigrid method for real-time simulation of deformable objects. Deformables are everywhere in our real world. My clothes is deformable, or hairs are deformable. If you punch me in my face, you may also find it deformable. They are also essential elements in the virtual world, providing us nice experiences in many applications, such as animations, games, or virtual surgeries. You name it. The state-of-the-art deformable simulators, such as projective dynamics, suffer from scalability problems that run slowly on large meshes, such as this octopus with 0.1 million tetrahedra. Our goal was to produce visually similar results with much better performance, like shown on the right. When talking about performance, let's first take a look at a common pipeline to simulate a deformable object. It can be as simple as this. You feed the current state as an initial guess to an optimization framework, and it spits out the next state for you. You keep iterating the states and finally get an animation. And to solve the optimization problem, a successive linearization is usually required, bringing the linear solve as the main bottleneck for most of the large-scale simulators. Many works has been done to accelerate this linear solve over a decade. For example, there are methods using prefactorized system matrix to approximate the real stiffness matrix, like projective dynamics. There are also methods trying to apply iterative solvers to the nonlinear optimization problem directly, such as position-based dynamics or the Chebyshev semi-iterative solver. The scalability of those full space approximation methods usually gets hindered by either a high memory cost or a bad convergence behavior. Subspace methods provide a very nice solution for fast simulations, since these methods restrict the size of the linear solves to be fairly small. However, the motion of the corresponding simulation is also restricted by the choice of the subspaces. The multigrid method, of course, is an intuitive solution when we want to solve large linear systems. Since our method is also a multigrid solver, here I'd like to elaborate it a bit more. The key idea of the multigrid is to only solve a linear system very crudely using a few Jacobi or Gauss-Seidel iterations, which are referred as smoothers, and then pass the residual to coarser levels to be further smoothed. Then the coarse level passes the correction back to final levels, and we do some extra post-smoothing to the system to get an approximated solution. The benefits of a multigrid structure come from two aspects. First, usually the solvers of coarse linear systems are cheaper compared to final level ones because they are smaller. Second, the iterative solvers are working as smoothers. They eliminate high frequency errors pretty well, and the low frequency error that a smoother cannot handle becomes a high frequency one in coarser levels. This is a holy grail of the multigrid method. Just keep in mind we are going to use this piece of information later. So how do we set up the multi-resolution problems? We can either set up the problems geometrically from rediscretization of different resolution meshes, but that needs some expertise to set up and is currently limited to regular grid structures. Or we can use Galerkin projections to recursively set up the A matrices. This one is much simpler to set up, and it should work for any meshes and any restriction and prolongation schemes. However, it just does not work well with trivial picks of U matrices. What we want is to inherit all the nice points from Galerkin multigrid's methods and make it scalable. Now the U matrix is a prolongation matrix that passes coarse level correction into the final levels. We'll also use U transpose as a restriction matrix that passes the final level residuals to coarser levels to make the entire system symmetric. So let's see, how do we build our multigrid? To build this, we first uniformly sample the coarser level vertices from final levels using furthest point sampling. And then we want to build an interpolation scheme that can be used to pass the information between levels. As we know that the U matrix is an interpolation matrix that determines two things. First, It decides the degrees of freedom of coarser level nodes. What kind of information do we want to interpolate, all right? And second, it decides the interpolation weights, which is how we interpolate. The key idea of our method answers these two questions exactly. To be more specific, we allow coarse level nodes to move in a higher dimensional coordinate, and we use piecewise constant weights to interpolate them. We first lift the degrees of freedom of a coarser level nodes from 3 to 12, which lies in a affine transformation space. We called it a scaling space coordinates because we were inspired by Alex's 2012 SIGGRAPH paper, the fast automatic scaling transformations. This space encodes more geometrically meaningful information such as scaling, shearing, linearized rotation, and translation compared to the traditional positional space. And we find it particularly useful to cut down the size of coarse grid more aggressively, typically an order of magnitude smaller. And the second thing we want to do is to decide the interpolation weights between two resolutions. Here, we are only going to use piecewise constant weights, which is a kind of counterintuitive. But why? Well, we actually try smooth weights at first, but they have problems. Let's say there are two nodes now, V1 and V2 from the fine level. And V1 is smoothly controlled by N coarse level nodes shown in red, and V2 is controlled by M coarse level nodes shown in blue. Any edge between V1 and V2 in the fine level, which is one single non-zero in the matrix, will end up with M by M non-zeros in the coarser level matrix UTAU. This is very common to see in an unstructured mesh, making the sparsity of the coarse level matrices much worse than it should be. And those non-zeros will be passed further into deeper levels, causing many issues in the memory footprint. We can see this problem more clearly in an actual matrix with 117K rows and columns and 10.4 non-zeros per row on average. This is the fine level matrix. When interpolated using smooth weights, the coarse level matrix, which has only 4.k rows and columns, will have, on average, 193 non-zeros per row. And our choice of piecewise constant weights will reduce the number to 37. Notice that this is only a 2-grid V cycle as a toy case. When we pass those non-zeros into denser and denser coarser level matrices using smooth weights, it will hurt the performance of coarse level solves a lot, while our choice of piecewise constant weights will end up with more than 20 times faster compared to smooth ones in a big V cycle. But what do we lose? Piecewise constant interpolation is supposed to be bad at scaling, right? Well, let's see how bad it is. Let's say now the blue thing is our fine level mesh being controlled by only two green dots as the coarser level nodes. If we move one green dot upward, a smooth weighting scheme with linear blending looks okay-ish, while the piecewise constant weights tear it apart. That's the reason why people always say piecewise constant interpolation is bad. But we find the cliff caused by piecewise constant weights is not that bad in our multigrid scheme. The error it created compared to the exact solution looked like an impulse function, which is extremely high frequency. Remember that high frequency errors are easy to remove when applied with some smoothers. We observed that the piecewise constant weights might be bad at scaling, but they are acceptable in the multigrid framework. As a result, we choose to stick with the piecewise constant weighting strategy. Because this one is the key to maintain the sparsity of our coarser level matrices without causing too much troubles. Moreover, it is also the key to enable us to update multi-resolution system matrices efficiently when the finest matrix A has changing numbers. To bring everything together, we follow a Galerkin multigrid pipeline with our choice of U matrices. There are some more details about the acceleration of constructing the multi-resolution matrices and regularizing some degenerating cases, but I don't think I have time for those. So please refer to our paper for more details. Our method is not assuming a specific shape of multigrid cycle. You can use a deep V cycle or a wider W cycle without changing anything. We are also not favorable towards any specific nonlinear optimization scheme. We can run the quasi-Newton or ADMM or Newton's method as well. For example, here we showed an example of running Newton's method to simulate a close with 0.4 springs at real time. It can handle dynamic matrix change caused by the nonlinearity of the mass spring system at the collisions as well, generating vivid wrinkles. Here we show the examples we had in our paper, ranging from thousands to nearly 1,000,000 elements. All of them are running in real time in a single NVIDIA 2080 card. And the pre-computation time is under 30 seconds, which is not a terrible number. Those times are used for sampling the coarse level nodes, computing the U matrices, and allocating memory space for the multi-resolution A matrices. To visually test the scalability of our method, we simulate a Hanning armadillo with the same material but different resolutions, and they look quite similar. We plot the memory cost in the red graph and time cost in the blue one in a log-log scaled plot, where the x-axis is the number of tetrahedra. Here we also draw a green line, which is a line with slope equals to 1, indicating linear behavior. We see that the memory cost of our multigrid solver scales linearly, which is very nice, and the performance scales better than linear initially with the help of parallelization, and it will eventually converge to linear for large meshes. We also validate our choice of an interpolation scheme using the armadillo example with 44 degrees of freedom. Here, we pick a 2-grid V cycle where the coarse grid solves this linear problem exactly. We use the error reduction rate ρ to see how good or bad our choice of U matrix is. ρ is the ratio between the error after the coarser level solve and the error before it. Of course, we are not expecting ρ to be 0, which is too good to be true. We still want ρ to be as small as possible to see the power of multigrid. We first test the effects of using scaling space coordinates in coarser levels. We can see that our method on the first row produces much better error reduction rate compared to using positional space DOFs. Well, to make it a more fair comparison, we can increase the number of coarse level vertices to 400 to make the total degrees of freedom the same with our method, and still we can see that the choice of scaling space coordinates does matter a lot to reduce the error an order of magnitude smaller. We'd also like to see how bad our method is compared to smooth weights. Thanks to the smoother, our interpolation schemes produces 3 times worse error compared to the smooth one, but since it runs 20 times faster, we still pick the piecewise constant weights in the end. We compare our method with other GPU methods based on iterative solvers. The blue curve is our method, the green one is a Chebyshev semi-iterative method, and the red and pink ones are the Vivace solver running with different Gauss-Seidel iterations. As we can see, when terminated at 33 milliseconds, our method reduces the relative error much better. And in order to reach the same amount of error, it will cost the Chebyshev more than 300 milliseconds to run and the Vivace more than 500 milliseconds. We also visualize this kind of difference. Here, all simulations are produced by projective dynamics with different solving strategies. The top left one is a ground truth produced by prefactorization in vanilla PD. The top right one is using our multigrid solver, which resembles a ground truth solution a lot. The bottom two are Chebyshev and Vivace solve, where we fine-tune the simulation parameters to their best performance. You can still see that the early termination of these methods causes the octopus look much stretchier than it should be. With our method as the backbone of linear solve, we can interact with a deformable dragon with 0.7 million elements at around 40 frames per second. Well, let's summarize our talk today. We aim for a fast deformable body simulation, and we can choose any nonlinear optimization framework to begin with, such as Newton's method, or projective dynamics, or ADMM. We apply a multigrid solver to solve their linearized systems based on Galerkin projections. And eventually, we show that our construction that uses piecewise constant ways to interpolate the scaling space coordinates is able to elevate the entire problem, making the real-time deformable simulation scales to another level. Of course, there are limitations of our method. The biggest limitation of our method is to handle topological changes of a mesh during the simulation, because that will end up with new set of U matrices, and the repeating the pre-computation of our method prevent us to keep its real-time performance. We are also currently assuming homogeneous materials, so we sample the multi-resolution nodes only uniformly. When a heterogeneous material is wanted, some smarter picks of the multigrid is needed. Last but not least, we sincerely express our gratitude to our friends and colleagues for many insightful discussions, to Yuxiao Guo to help us with lots of useful CUDA programming tips, to Huamin Wang for providing his GPU simulating framework, and to all the reviewers for their valuable feedbacks. Well, that should conclude my talk today. Thank you very much for listening. We also have our source code available online right now. Feel free to try it on your need. Thank you.